Hello and welcome to One-on-One. I'm Vernon O'Reilly Ramesar, and I'm very pleased to say my guest today is actually a first for me. Professor Stephon Alexander, who is the Ernest Everett Just 1907 Professor of Natural Sciences at the Physics Department of Dartmouth University. Theoretical physicist, welcome to the program.
Pleasure.
As I was telling you before, particle physics is a particular fascination of mine, so it's a big thrill having you here. And of course, you're the only guest I've ever had who has something in common with President Bill Clinton, Dr. Brian Cox, and you've also met Stephen Hawking several times. So what an interesting field you work in. And the reference to Bill Clinton, of course, is the fact that you're also a saxophone player.
Yes.
And it's a great passion of yours as well.
That's right.
But let's talk about the idea of theoretical physics. We're living in a very exciting time for it, aren't we? I mean, recently we had CERN announcing that they may have found the Higgs Boson particle. What does this mean for you as a theoretical physicist?
Oh, it's pretty much the discovery of the Higgs Boson is, which I would like to say a little bit more about. So the discovery of the Higgs boson is a big deal for me because, first of all, my field interconnects two subfields in physics, which is particle physics, or what we call elementary particle physics, studying the very fundamental nature of what matter and energy is, what things are really made out of, and cosmology, which is the universe as a whole. So one question that we like to ask is, how are the smallest things in the universe, quarks and atoms, electrons, connected to the largest things in the universe, what we refer to as a space-time fabric. And when I was a PhD student about 1996, in the middle of taking one of the graduate level courses, one of my professors, Gerald Goralnik, would oftentimes complain about this particular theory that he worked on in 1964. This theory that he worked on with Peter Higgs and Tom Kibble while he was at Imperial College was patchwork, so to speak, a theoretical idea to try to figure out how to give mass to these elementary particles. I mean, the things that you and I are made out of. Electrons, quarks, okay, which makes up the proton. These objects actually should have no mass whatsoever. Now, the consequence of that is if something has no mass, that means it's free to travel at the speed of light. Therefore, the things that we're made out of, if it had no mass, we just evaporate in a split second.
Right.
So, in the 60s, we had a very good idea of all of the elementary particles that make up nature, but we had no physical mechanism of giving them mass. So my professor in 1996 was one of the people, the co-inventors of the Higgs boson. And he would complain, this theory, it's wrong, and it's amazing that in 2012, it's actually a real thing. It's discovered, it's there.
In fact, Stephen Hawking himself was surprised that it would be discovered in his lifetime.
That's right. And the thing that is amazing about this, the reason why, turning this back to my field and what my research involves, which is connecting fundamental particles, the most microscopic objects known to us, to the universe as a whole, it turns out that the Higgs boson is a field, actually, that's a cosmic field. It fills the entire universe. Now, it's not visible to us, but we know of its existence because, you see, if I drop this cup, if I let this cup go, it will drop. So the force of gravity attracts this cup to the Earth because this cup has mass. The Higgs field is a field that at every point makes sure that this cup has mass. And it's everywhere. It fills the entire universe. So this is actually the entity that we know exists today that actually fills the entire universe and interacts with the most subatomic particles. So this is a great discovery, and it's very important for my research because it connects the entire universe, the largest things in the universe, with the tiniest things.
It's interesting because you're a theoretical physicist, and of course that means you work in theory, which is there must be something that exists like Higgs boson. We presume it exists because everything is sort of tied together and things have mass. And then when you reach a stage where Syrian and other places have discovered, okay, we think we've actually got it, it suddenly concretizes a theory, doesn't it? Is that what your whole field is about? It's like reaching little benchmark of saying, okay, this theory is now established.
Yes, and that's, I mean, imagine that, you know, these six physicists, theoretical physicists in the 60s had a theoretical idea. They wrote down a mathematical model, having no idea whether this would have anything to do with reality. Yet these mathematical equations predict the properties of all the elementary particles and also the property of this unknown thing. I have a colleague, Professor Jim Gates, who would like to say that being a theoretical physicist is like being a composer on a planet with no sound and being asked to compose music. So this is kind of the game that we're in. We're kind of almost blind men in the dark trying to make a discovery, and we sometimes have to wait 50, maybe hundreds of years for our theoretical ideas to come to fruition.
Because also sometimes science has to catch up with your theories, doesn't it?
Absolutely.
For you to be able to have the equipment that would be able to detect.
Right, and you have no idea the kind of crazy stuff we're thinking now.
But I mean, people will describe the field you're in as sort of airy-fairy, but in fact it is so elemental to everything else in science and the reason we exist on the planet, or why the universe exists.
Exactly. I mean, for example, quantum mechanics. Quantum mechanics is the physics or the mechanics of the subatomic world. We also have very good reason to believe that these laws operate on even macroscopic scales. And quantum mechanics is a very strange theoretical idea. It basically says that, you know, an electron, it's possible to be two places at once. Things can go through barriers. Almost, you know, matter can have these ghost-like type properties. So who would want to believe in such a crazy idea? Except that most of our technology is based on quantum physics. The integrated circuits, the transistors that underlie that are based on quantum mechanics, superconductivity, your cell phone. So most of our technology, lasers, is all based on this weird type of theoretical idea.
So in terms of the average person wondering what's the applications for this, you mentioned, in fact, it does translate quite often. And so when you hear of billions being spent on a collider, for example, a large hadron collider, it actually is money that is well spent, isn't it?
Absolutely. Because every time we spend billions of dollars to build a detector to first of all, generate the highest amount of energy that we've ever created on Earth, it pushes the human mind, it pushes our collective talent to develop new technologies that spin off into other applications. So, because that's, you know, we're pushing ourselves to make this science work. At the end of the day, I think the fundamental drive of humans is our natural innate curiosity. And that will always rise us to a high level of performance and innovation. So that's one thing. The second thing is that we sometimes don't know where an innovation for a technological application will be. Sometimes just in the pursuit of just understanding something fundamental about nature, pursuing our curiosity, will naturally lead to a technological innovation. This has happened countless amount of times.
If we look at the space program, people thought it's money wasted, but in fact, a lot of things we use today came out of the space program initially.
Absolutely. The GPS device, for example.
Teflon, even.
Teflon, that's even better.
And we of course just landed the Mars rover, which is pretty exciting as well. So we look at things that are going on in outer space, but when you think about the idea of us here on Earth being able to take two particles, subatomic particles, and smash them into each other at a speed that is really difficult for us to comprehend, that's also pretty impressive as well, isn't it? But for some reason, the public doesn't quite get as excited as they would about a space mission. Yes, and I think that makes sense because, you know, space is out there, right? I mean, we're here on Earth, you know, you have to drive your car or, you know, walk somewhere from point A to point B. Space is out there. What does it have to do with me? And I think that, you know, some of us are just naturally fascinated by space and some of us are not. I think that it does capture our imagination. I think that a big part of why we exist is because we like to entertain our imagination. So I think that the more we get into space science and we understand that actually it is connected to us being here on Earth, And you work in both worlds yourself?
I work in both worlds. I mean, sometimes...
So one is looking outward from our planet, and the other is actually looking very deep inward into the very essence of what matter is.
That's right. It's interesting that, you know, I was in India not too long ago, and was talking to an Indian physicist, and he was telling me about some really interesting Hindu philosophy that believes, I mean, some particular part of Hindu philosophy that I don't quite remember now, so I can't do too much justice, but the basic concept was that what's way out there in space is also the same as what's way in. So I found that to be quite a beautiful idea.
And the old expression, we're all made of star stuff.
And in fact, it is absolutely true. We are made of stardust. I mean, a star basically is the engine that manufactures the heavier elements, metals and carbon, oxygen. And after that star died, it became planets, and we are, you know, we came from the Earth, and we were made up of our molecular structure it was produced in a star.
In terms of how science and religion often collide, do you see any sort of problem in the two coexisting peacefully, if you will?
I have no problem with science and religion coexisting, because science is actually not about saying, oh, I know something, I understand everything. I mean, science is actually about humility. Science is about not knowing. So it's about, yes, we know something very well. We know it so well, we can make a cell phone work. Okay? We can make an airplane do automatic pilot landing, right? However, there are things that we don't know, and a scientist is supposed to keep an open mind. And I think that, you know, even in religion, the notion of faith is about keeping an open mind. So I think that there is space for both to coexist.
And of course, science is also about constantly evolving knowledge, isn't it? I mean, we work with things like gravity, for example, and we have a fundamental understanding of it. We know how to work with it and work around it sometimes to get off the Earth. And yet, there's things about gravity we don't quite fully understand yet, aren't there?
Yes, you know, the most familiar force is gravity. I mean,
when we fall on our face, yes.
You do the experiment all the time, you know, is actually the most mysterious force known to us, because gravity is not just what we think it is. It's not just a force that pulls massive bodies together. Albert Einstein actually taught us that what gravity really is the bending or the warping of the space-time fabric. And the fact that you see a cup moving towards the Earth is not really a force per se. It's experienced as a force, but it's really the warping of the Earth, the fact that the Earth warps the space-time fabric. And it has other really remarkable properties on top of a force. For example, you could have something called a gravitational lens. If you look into outer space and you see, you look at a galaxy very far away from us, you'll see 4 copies of the same galaxy, because another galaxy in front warps the space-time fabric to create a kaleidoscopic effect. So you think you're seeing 4 things, but it's really one thing. And that's real. I mean, we have real pictures of that.
A lot of it really boggles the mind, doesn't it, when you think about it? In terms of your role as a physicist, you obviously are a dynamic, charismatic person. It's important that we have people like you, people like Dr. Brian Cox, for example, and the late Carl Sagan, to try and let the average person understand this very complex world in somewhat of a simple way, isn't it?
Yes.
Because it really is beyond most of our understanding.
Yeah, it is definitely beyond most of our understanding. I think that there are some things about nature and about even the physical universe that might be beyond the mind's ability to comprehend. But it doesn't stop us from, continually pursuing. And I think also, when I sit down, I just talk with friends, over a carrot.
And we should mention you were born here, you grew up in the States.
That's right. I was born in Trinidad. I left when I was 8, and I grew up in the States.
Well, the Bronx is kind of like Trinidad anyhow, isn't it? So,
the Bronx is, we have roti there, It's not as good as a roti here, but...
So in terms of expressing to the public what you're doing, it is important, otherwise it comes down to even things like funding from politicians.
Yes, it's important, it's fun, and also I get a lot of great ideas from talking to the public. I gave a public lecture yesterday for NIHERST, and the students, I mean, these are Caribbean students, I was so impressed. I was so impressed with the depth and also the intellectual curiosities in their questions. And those questions really, sometimes you want to, we're so busy thinking, professional physicists, really complicated ideas, that sometimes the simplest question is the one that can lead to a breakthrough. This is what led Albert Einstein to his discoveries. He asked these baby questions. What does it feel like to ride a beam of light? You know, if I'm in an elevator and I'm, you know, dropping, you know, and can't see outside, why is that situation indistinguishable from being in an elevator on Earth where the elevator is not moving? These were the kind of questions that led to these major revolutions. And of course, the amazing technological outcomes of those revolutions.
In terms of popular culture, I mean, obviously film has dealt with things like space for a very long time. It's been a fascination for a lot of people, sci-fi.
Yes.
Is that something that you sort of look at and cringe sometimes, or do you think it's a look at the possibilities that exist, for example, with 2001: A Space Odyssey, for example, if you look at a movie like that? Do those inspire you, or do you just shake your head?
I'm a big sci-fi fan. In fact, when I was younger, it was because of my fascination with sci-fi and comic books and video games as a as a teenager that led me into becoming a physicist. In a lot of ways, doing the kind of things that I do as a physicist, I feel like I'm doing sci-fi. Because the universe actually, when you start delving into how the universe operates, it's really a bizarre, fascinating place. And in a lot of ways, we have the idea of time travel. Mm-hmm. These ideas come from theoretical ideas in physics. In Star Trek, you have these wormholes portals that you can jump through to get you from one distant place to another distant place. These are all theoretical ideas coming from physics.
And the ever-problematic warp speed, of course.
Of course, yeah. The cosmic string.
In terms of your great influences in your life, scientifically, who would they be?
Well, of course, there's the usual greats, Albert Einstein, Richard Feynman. But, as a young person pursuing physics, there are many of us from Caribbean origin. And I discovered, my dad, Keith Alexander, used to always mention this really bright man from Trinidad, Rutrath Capildeo. Mm-hmm. And so I started doing research on him. When I did my first postdoctoral work at Imperial College in London, so when I was in London, I pulled out one of his papers. And I'm looking at this paper that he wrote on relativity. A lot of our science that we have that takes us out into outer space, he contributed to that. So we actually have a son of the soil that contributed to this human quest for space exploration. So just, he was a very big role model to me, just to see that we are capable, a Trinidadian was capable of doing the highest level of science. And so that was important for me to know.
So he was an inspiration for you?
He was a big inspiration for me.
I guess one of the problems with physics, and you've got the sense that you're dealing with very large things, very small things, understanding the basics of why we are here. And yet, almost all of it comes down to mathematics, doesn't it?
Yes.
And I think that's where a lot of people get confused. How does E equal mc squared mean anything, for example?
Yes. Thanks for asking that question. So our basketball court, so to speak, when we do physics, when we're actually in the moment of doing physics, doing research, as a theorist, is mathematics. So basically, I'm pretty much a mathematician. But one of the things I like to tell, especially my students, is that the kind of mathematics that we do in physics, of course, can range, and the physical discoveries we make can lead to new mathematics. So sometimes we have to invent the mathematics as we go along. But the mathematics is not to be mistaken with rote mathematics, 1 + 1 is 2. Mm-hmm. Sometimes what we do is that we have the equations are similar to when a musician looks at a score of music and smiles. When we look at our equations, they look very beautiful to us because we can see relationships and symmetries that relate one equation to the other equation. So when you say E is equal to mc squared, I don't actually see these symbols. In my mind, I'm trained to see a light cone. I see a geometrical pattern, okay, where the energy is related to the speed of light, okay, through this geometrical relationship of of a cone, okay, which represents how light propagates.
So for example, with Higgs boson, that would have been, somebody would have written an equation and said, okay, well, that makes sense as I stand back and look at my chalkboard, and that would equal to that.
Yes.
If this missing variable here suddenly became real. Yes. And that's when you theoretically realize, wait, this must exist because this equation makes sense because that variable exists.
It's detective work, exactly. It's like if if you're investigating something, or you want to know where your child is, he's supposed to be home at some time, and you say, well, he can't be here, he can't be here. I mean, there's a really good chance that he's with his friend over, because I called the other friends. It's the same type of thinking, as you said. Right. It's really detective work. So that's right. We have this equation.
So you're ruling out this, that, and the next thing, and saying, well, if they don't exist, then this must necessarily
exist. This must be the case. And we use a lot of symmetry in our reasoning as well. If I look at this thing in this way, it must look the same, because experimentally we see that these particles are related to each other by looking at them in different ways and seeing the same thing.
So for the average person who was following the news and heard about CERN colliding particles and thinking they discovered the Higgs boson field or particle, or the God particle as it's called, explain to us exactly what happened there. Like, how would they observe something like that based on two particles being smashed to smithereens?
Yes. So it's actually that type of physics, how a particle collider works, is actually quite simple. So let me say a few words of how that works. So many of us have played with magnets as kids, okay? So I take, let's say, can I use a cup?
Of course you may use my cup.
So let's pretend this one cup is a magnet, and this other cup is another magnet. So let's say I put two north poles together, and I bring this magnet closer to the other magnet. This one will move away. That's the usual thing.
Right.
Well, that is the physics behind these particle colliders. So the Large Hadron Collider,
which you should mention is kilometers around. It's huge.
That's right. Yeah. It's huge, and we accelerate them. Okay, we accelerate them with an electric field, because they're charged particles. The same way you can move electricity through a wire, we apply an electric field to accelerate them. And then one is accelerating the other direction, and then at some point we allow them to collide, bang on. And what happens is the following. These particles, when the proton, so a proton is positively charged, the other one is positively charged. But protons are actually, we now know very precisely that protons are really made up of three constituent other particles called quarks. So these three quarks are sort of an atomic orbital around each other that make up a proton, another quark. And as these things collide, and they hit each other, the quarks collide as well. When these quarks collide at this very high energy, they can decay into other particles, okay? This is just the physics involved. Particles, heavy particles, can decay into lower particles. But if these particles have very high kinetic energy, they can also create, a heavier particle. So from energy conservation, I can create higher energy particles, and one of those particles could be the Higgs particle, the Higgs boson. A boson is just a particle that has integer spin. So you can, by colliding, you have this other thing. But how do you know it's a Higgs boson?
Well, that was my other question. Right. I mean, how do you look for it?
Yeah, how do you look for it? Well, you look for it by excluding the other things. So you might see a Higgs boson, but then as you smash these protons together, it produces derivatives of other particles. Now, these other particles are charged as well. So you have to select, in other words, filter them out, okay, and make sure that you've said, oh, this is an electron. So all the other known particles that are produced in this collision, you have to make sure that you select for that. And the way you select for that is by having a magnetic field, okay? And what happens is that we know from basic electromagnetic theory that a particle that has electric charge, in the presence of a magnetic field, the magnetic field will deflect will exude a magnetic force and deflect this charged particle in a very definite way. So based on that deflection, it's like, you know, Brian Lara hitting a cricket ball, right? We know exactly where it's going to end up, and we detect it and say, ah, that's an electron. This is a muon particle. And then we collect all of this data, say, well, there's some missing energy, all right? And based on that, we can deduce whether it's a Higgs particle. Another way you can do it is that if you produce this Higgs particle, our model, very precisely, the standard model, what we call, that includes a Higgs particle as a mathematical thing, there's an equation that tells you exactly how the Higgs particle will decay into two light particles, particles of light. We call this two photons. And we can detect that because we can detect light. So the Higgs, by decaying, so just to summarize, protons collide, bang, you produce a Higgs particle. The Higgs particle decays into two photons. You detect the energy of that photon. And if the energy, okay, is exactly, agrees with what the theory says, you know you have something like the Higgs. But then we have another way, other ways of doing it, and you cross-check those other ways, and that's the way you decide.
And yet they still held a press conference and said, we may have discovered.
We may have discovered.
Because there's still a little element of uncertainty.
There's still a little element of uncertainty, but most of the community, it's very hard to say it's not
You're still
the Higgs.
dancing right now.
Yeah.
Well, it's been a fascinating half hour already, and I wish I had like 3 more hours to talk to you.
Wow, time flies, you know.
I know. Well, there you go. Thank you so much, Professor Alexander, for being here. A great pleasure having you on the program.
Thank you.
You've been watching One on One. Join us again tomorrow for another edition.